This video provides you with an introduction to complex numbers. We use complex numbers to deal with negative numbers under even index radicals. The imaginary number I is defined that I equals the square root of -1. And from that, we can conclude that I squared is equal to -1. The set of imaginary numbers consists of numbers of the form bi, where b is a real number and b does not equal 0, and then I, well, that's the square root of -1. So we use this imaginary number I when we have a negative radicand under a square root. Let's consider the square root of -a. Well, -a can be rewritten as -1 times a. And our product rule for radicals say that we can break this up then into the square root of -1 times the square root of a. And we just define the square root of -1 to be equal to I. So this would be equal to I times the square root of a. So how do we get from here to here without all the extra steps? Well, simply take the I out, or the negative out, and put an I in front. So to simplify a negative radicand under a square root, you're going to start by taking the I out and making the square root of -a equal to I square root of a. From there, you want to simplify the radical with a positive radicand like we do normally. So let's simplify the square root of -16. As soon as I see that negative under a square root, I'm taking the I out. This becomes I times the square root of 16. And then we simplify the radical like normal. Square root of 16 happens to be a perfect. This becomes I times 4. But we want to write it in the proper imaginary form, which is bi, where b is the real part. So we're going to rewrite this 4i. Let's simplify the square root of -50. As soon as I see that negative underneath my square root, I'm taking an I out. This is I times the square root of 50. And now we want to simplify the square root of 50. It's not a perfect, so we're looking for the largest perfect square that's a factor of 50. That'll be 25. It goes in 2 times. Don't forget to bring the I down. So we're going to have I times 5 times the square root of 2. But the way we normally like to write this is either 5 square root of 2 and then the I afterwards. That's ideal imaginary form, but I don't like to write it that way because it can be ambiguous whether the I is underneath the radical or not. So frequently you'll see it written 5i square root of 2. Let's simplify negative square root of 36 plus square root of -49. In the first part of this example, we have a negative, but notice it's not underneath the radical. So an I is not going to appear. We're just going to have a negative out in front. And we simplify the square root of 36, which is a perfect. It's 6 plus. In the next term in this example, the negative is underneath the radical. So that tells me that we are going to have an I, and then the square root of 49. We want to simplify the square root of 49. It's a perfect, it's 7. We end up with -6 plus 7i. In the next example, we're going to start with the square root of 8. That can be simplified. We want to find the largest perfect square that's a factor, and that's going to be 4. It goes in 2 times, so the square root of 8 simplifies to 2 square root of 2. Now we need to deal with this square root of negative 32. There is a negative underneath the radical. Right away, we want to take the I out. Then we simplify the square root of 32. We're looking for the largest perfect square that's a factor of 32. It's going to be 16. Goes in 2 times. Square root of 16 is 4. This turns into 4i square root of 2. You will notice that these are like radicals, both square root of 2, but what we have in front of the square root of 2 are not like terms. 2 and 4i cannot be combined, so we're going to leave it just like this. 2 square root of 2 minus 4i square root of 2. In our first 2 examples, our solution just ended up being one term, and that term had an I in it. These are basic imaginary numbers. It has a real portion and an I all in one term. These last 2 examples, our answer was 2 terms. The first term in each example is a real number, negative 6 and 2 square root of 2. They're just real numbers, no imaginary part. But then the second term contains an I. Numbers that are of the form a plus bi, where a and b are real numbers, and I equals the square root of negative 1, these are called complex numbers. The number a is the real part of a plus bi, and bi is the imaginary part. So if we scroll back up and look at these, we can see here's the a, and then plus bi. Here's the a, and plus bi. First term is the real part, the second term is the imaginary part. I'm sure you've seen a diagram very similar to this involving real numbers. And we've been told up to this point that the real numbers is the largest set of all numbers. Well, that is not the whole truth. The whole truth is that the complex number system is the largest number system. Complex numbers that are of the form a plus bi contain real numbers and imaginary numbers. This portion right here is the diagram that you're used to seeing. All right, there's just a little more to the story. So you'll see that complex numbers, it's the big rectangle around everything. And then within that, we have the set of real numbers and how it breaks down like we already know. And then off to the side, we see the set of imaginary numbers. I just always like to give you guys the whole truth to now know that the complex number system is the largest number system, and that is never going to change.